Why do some things dissolve in water while other things don't dissolve in water? Well, that's the big question for today. Welcome to AP Chemistry Unit 3.10, all about solubility. In this episode, we're going to try to mix some things together and see what dissolves in water and what doesn't, and we'll try to make sense of it all, thinking about their intermolecular forces. Then we're going to take a look at some AP-style questions, the likes of which you're probably going to be asked. So grab your goggles and apron, and let's get started. Let's start with our essential knowledge statement for this section, and it's a very short one. Substances with similar intermolecular interactions tend to be miscible or soluble in one another. We learned, back in Unit 3.1, that there are several types of intermolecular forces, starting with nonpolar molecules. Nonpolar molecules tend to make London dispersion forces. That's their main intermolecular force, and it's very weak. As a result, nonpolar molecules tend to want to hang out with nonpolar molecules if they want to hang out at all. Next, we have polar molecules, which exhibit dipole-dipole interactions. Those are stronger and cause the molecule to have a dipole, sort of a negative end and a positive end. And polar molecules tend to want to hang out with other polar molecules because they can line up their positive and negative ends like little magnets. And the third type of intermolecular force is hydrogen bonding. And that occurs, it's like a strong dipole-dipole force occurring when hydrogen is attached to an oxygen or a fluorine or a nitrogen. Those bonds are superpolar and they create really strong dipoles and a stronger intermolecular force as a result. So if you need a quick refresher on intermolecular forces, go ahead and head back to section 3.1 and then return here. I'm just going to throw out a question. This is a very typical type of question. It says, which substance is the most soluble in water? All right, we know that water is polar, hopefully. And when I'm looking at this question, I have to decide which of these things is actually polar or not. And so let's do a quick review of how to determine polarity. Again, this is from Unit 2, so if you need to determine polarity, head back there. How to determine polarity? First, you need to draw the Lewis structure. The problem I just showed you, there was no Lewis structure drawn, but there were 4 choices. So if you can't visualize the molecule, and there's no shade there, just go ahead and draw them. Just draw them, make sure you have the Lewis structure because we determine the Vesper shape from that. And we use electronegativities to determine if the bonds are polar or not. If they're polar, determine if they sum to an unbalanced molecule or an asymmetrical molecule. Usually, lone pairs on that central atom often indicate a polar molecule. So if you don't know if it's got lone pairs, just draw it. All right. So for example, here we have a couple of molecules that are polar. If we draw the Lewis structure, we would see lone pairs there and there. So we get net dipole. They look a little wonky. Whereas something like this is going to be nonpolar because the silicon does not have any lone pairs on it. So you'll need to know how to do that. And we can get it into some more complicated molecules. You'll see some organic molecules here today, and benzene might be one of them. But benzene, even though it contains carbons and hydrogens in this circle, it ends up being nonpolar because neither end of the molecule is more negative than the other one. But here's a few that are polar that contain carbon and hydrogen, and you'll see that they often have nitrogens and oxygens in them. This one happens to be just a bend shape. But you can see that the ends of these molecules are different, and so they end up being polar as well. So what does this have to do with solubility? Well, it turns out we have a fancy little phrase we like to use called like dissolves like. And it basically goes like this. Polar molecules will dissolve in other polar solvents. So they like to hang with each other, so something that's polar will dissolve in another polar, like water, for example. Nonpolar molecules will dissolve in other nonpolar solvents, like to hang out with each other, but polar and nonpolar do not mix, for the most part. Though polar solvents like water can actually kind of induce dipoles in nonpolar solids getting a small amount to dissolve anyway. Let's go through the steps for how to determine what solute is soluble in which solvent. So I try to use all those vocab terms in one sentence. This is my main page of notes, so if you need to pause the video for a second or take a screenshot, go ahead. Draw or be given the structures. Always start with the structure, even if it's not given, take the time to draw it, because you need to know if it has lone pairs. Determine whether each molecule, including the solvent, is polar or nonpolar. So you have to be able to compare. For small molecules, determine the polarity based on that central atom. So draw the Lewis structure. If it's got a lone pair or two, it's probably polar. And if it doesn't, it's probably nonpolar. But you kind of have to know those rules as well. For example number 1, we took 2 test tubes and added a small amount of water to them. To the first test tube, we dropped in a little bit of copper chloride, which is an ionic solid. And to the second one, we dropped a little bit of lead chloride, another ionic solid. Both copper chloride and lead chloride are ionic solids, but the copper chloride dissolved in the water mainly because it has weak ionic bonds, while the lead chloride did not dissolve in water because it has strong ionic bonds. So when it comes to ionic compounds, you kind of just have to know your basic solubility rules in order to tell whether something's going to dissolve or not, and we're going to talk more about those in Unit 4 when we do our chemical reactions. Just another day in the chem lab. And that brings me to my first note on here that ionic formulas are generally written as empirical formulas in lowest terms. So they look like they're small molecules, but you have to notice that they're ionic. And then ionic substances will dissolve in water, but not nonpolar solvents. So as long as the solubility chart tells us that they are soluble, they will dissolve. Insoluble ionic compounds don't dissolve in water because they have those strong ionic bonds. So if you recognize an ionic compound trying to dissolve it in water, you just have to know those solubility rules. For our next example, we lined up 6 test tubes in a rack, and we added water to all 6 of them. So we started with some water. In the first test tube, we added some methanol. In the second test tube, we added some ethanol. And the third one, we added some propanol, and then butanol, hexanol, and finally 1 octanol at the end. My first 3 alcohols, methanol, ethanol, and propanol, all completely dissolved in the water. You can see the propanol here has just made one homogeneous solution with the water. By the time we get to butanol, though, the butanol is only sparingly soluble in water, and even if I try to get it to dissolve, it will separate back out. Hexanol is even less soluble in water, and by the time we get up to octanol, which smells terrible, by the way, we get the octanol having none of it, and it's just in that layer at the top. This brings us to our next category on our notes. For organic molecules, like those alcohols, determine the polarity based on, first, whether the molecule is just an alkane, like methane, hexane, octane, and so on, and those names will end in ane, and they are nonpolar, so they will not dissolve in water. Whether the molecule contains a carbon chain attached to a polar part. Usually it's OH, could be something else, and that makes it a little bit polar. And the more OHs you see, the more polar it is, more polar areas it's got, the better it's going to dissolve in water. And if you see those, the shorter the carbon chain, like methanol, it was more polar, so it dissolved in water very readily. The longer the carbon chain, like butanol, hexanol, and octanol, had a really long carbon chain with an OH just on the end, and that was less polar overall, and so it didn't dissolve in water. Okay? For our third example, we took a simple volumetric flask and added a little bit of water to it. Then we added a little hexane to it. And the hexane, which is less dense than water, was unable to mix with the water because hexane is nonpolar. And so we ended up with 2 layers, a hexane layer and a water layer. Then we dropped in a few crystals of iodine, pure elemental iodine, which is a diatomic molecule. And it sank to the bottom because it's more dense than water, and it just sat there, although you got some really cool little bubbles hanging on to some of them. After shaking for a short time, though, we found that the hexane layer actually turned a color, sort of a pinkish purple. And that was evidence the iodine was dissolving into the hexane layer, but it was still sitting at the bottom in the water layer, not dissolving in the water layer. And if we look at the structures of hexane, water, and iodine, we can notice that hexane happens to be nonpolar. It's an alkane. And iodine is also nonpolar because it's just got a single bond that has same electronegativities on both sides, while we know water is actually quite polar, and so it does some hydrogen bonding with itself. So the iodine was dropped to the bottom, and it tried to dissolve in the water, and the water wasn't having any of it. But shaking it around a little bit, giving it a chance to shake with the hexane was able to dissolve some of the iodine. And now it's time to look at a few questions. These are typical of the types of questions you're likely going to be asked. So let's get started. The phrase like dissolves like refers to the solutes and solvents of similar molar masses, polarities, phases, or bonding. And hopefully you got this one pretty quickly, and that is the similar polarities. So similar polarities, similar intermolecular forces, and similar solubilities. So which substance is the most soluble in water? We're starting with this one because note they just listed the formulas and no Lewis structures. So unless you have been around these long enough and you can just know that they're polar or nonpolar, you should really go ahead and draw them. So I drew these real quick. And I look down the list and I'm looking for something that's most soluble in water. Water is polar. I have to know that. So I'm looking for something that's polar, and I see this one's kind of polar. It's got a chlorine off to one side. These two are nonpolar, and this is also polar. So wait, I have two that are polar. Okay, so what do I do? Well, I have to think about what type of intermolecular forces these are going to have. London dispersion. This is going to be a dipole-dipole force because it's polar, but it's not hydrogen bonding. This actually does hydrogen bonding because you have the hydrogen attached to the fluorine. So I'm going to pick letter D because it's got the strongest intermolecular force, just like water can do hydrogen bonding. Okay, first pause the video moment. A similar type question, again, just a list of chemical formulas, but this time we're trying to find the greatest solubility in pentane, which is a hydrocarbon at 1 atmosphere. So take a moment, draw them, pause the video, and see if you can guess. All right, now this one is a little tricky because we had to know that SiO2 is actually glass. It's not a simple molecule that we can draw, but it's glass, and that's not going to dissolve in our nonpolar solvent. The other three, we have a polar, a nonpolar, and a polar, and because that one's nonpolar, it will dissolve in the nonpolar pentane the best. Okay, which of the following molecules will not dissolve in water? So I got to think, not dissolving in water must be nonpolar. And I'm looking down the list here, and I see acetone, cyclohexane, pentane. Notice these both end in ane, and then both of them are shown down here. Alkanes don't dissolve in water. But let's take a look at acetone first just to see what it looks like. Hopefully your test giver will be nice and actually give you the structure of it. But acetone looks something like this. It happens to be a little polar because of that oxygen sticking out. And so it will dissolve in water, so that's not my choice. But I think both of these are going to not dissolve in water. Okay, your turn. Take a moment and try this one. Which substance is most likely readily soluble in both water and benzene, C6H6? So I got a polar and a nonpolar. Is there a molecule here that is kind of nonpolar but also kind of polar? Take a moment, pick your guess. And if you chose letter D, that would be correct. This is completely nonpolar, so it's not going to dissolve in water. This is an ionic compound. That'll dissolve in water, but not the nonpolar solvent. This one is acetic acid. That will dissolve in water, and it's very polar. This one actually has a nonpolar section and an OH on the end that might get it to dissolve in water. That's propanol, and we actually saw it dissolve just a little bit ago. All right, here's one that looks a little different. Tell whether each vitamin is more likely to be water-soluble or fat-soluble. Vitamin A and vitamin C, and they give the structures up there. So this one, we won't pause the video for this one. But notice they're pretty complex structures, okay? And you're looking for things that will help them dissolve in water or things that won't. First of all, over here, I see an OH on the end. That's great, wonderful. But look at all this area here that's just hydrocarbons. That's huge nonpolar section. And so that's probably going to hinder it dissolving in water. Over here, though, we got a kind of a nice little framework of carbons and stuff. But look at how many OHs are attached to this thing. That's got a lot of OHs that can do hydrogen bonding with water, and that is definitely going to be more soluble in water, while this one would be more soluble in fats. Okay, a couple more pause the video moments. Which pairs of substances will dissolve in each other? So you have to decide, are these polar and nonpolar, and which ones will go together? Take a moment, pause the video, draw them if you need, and meet you back here in a sec. And if you draw them, you find that this one is slightly polar, These two are nonpolar, and so these two will dissolve in themselves. That's 2 and 3, and my choice then is letter B. So hopefully you got that correct. If you did, congratulations. All right, all of the following will dissolve in water except we have 4 choices. Take a moment, another pause the video moment, why not, and see what you think. And I'm going to say that the first 3 are all going to dissolve in water. These are both soluble ionic compounds, and that's ethanol, and C6H6 is benzene, which is a hydrocarbon. And we'll end today's video. 2 more quick questions. This one showing 3 structures, and we're supposed to rank them. Correcting sequences correctly list the compounds above in order of their increasing solubility in water. So lowest solubility, medium, and high. And I'm looking over here and I'm seeing just a regular alkane. Here I'm seeing butanol with an OH on one end, and then this guy with an OH on both ends. Remember, the more OHs you have, the more soluble in water it's going to be. So this has no OHs, 1 OH, 2 OHs. So X, Y, and Z, I'm going to say, is my choice for letter D there. And the last one we have here is a pause the video moment. Why not continue testing ourselves, right? On the basis of molecular structure and bond polarity, which of the following compounds is most likely to have the greatest solubility in water? Not just soluble, greatest solubility. Take a moment, pause the video, draw them if you need, and meet me back here in a second. All right, I drew them, and wow, I got 2 polars and 2 nonpolars. These 2 are nonpolar, those 2 are polar. And they look really similar. So how am I supposed to decide which one of those is going to be more soluble in water? Well, most soluble in water look for hydrogen bonding. They look similar, but phosphorus and hydrogen make polar bonds. These guys make nitrogen attached to a hydrogen. That's a hydrogen bond. And that will bond most well with water and dissolve most well with water. And so NH3 is our choice. So here you have it, the main concepts of solubility, things dissolving in other stuff based on their intermolecular forces. I hope you found this helpful, and I hope you enjoyed the experiments. And in the meantime, if you have any questions, send them to me in the comments. And in the meantime, happy studying and have a great day.